My name is Professor Laura Rosella. I'm an Associate Professor of Epidemiology at the Da'Lana School of Public Health and the Canada Research Chair in Population Health Analytics. And I'm here today to give you some priming ideas or introductory concepts related to AI and machine learning. So the goal of today's lecture is really to get you familiar with some fundamental concepts. It's a big field, lots of terminology, lots of technical aspects, but I'm hoping in this first introduction that you get a really good overview of what machine learning and some aspects of AI are, why they're relevant for health, and what they aren't as well. So I'm going to frame some analytic approaches, give you some go into some key aspects of AI and machine learning, a little bit technical, just to get a good understanding of what the distinguishing features are of these methodologies, as well as go through lots of examples and applications, and also ask you to look at some examples yourself. So let's get started. So first of all, everybody knows that there's rapid growing interest in AI. And before anyone engages with this field, I recommend just sitting back for a moment and thinking about why that happened, because that really helps understand where we are today and where we're going with this technology. So the first and most important thing that's happened recently is an evolving data environment. And so what that means is that we had data that we have never had before. We have digitized data, including health records, which typically used to be paper-based. And we have new types of data coming from all types of smartphones, meters, social media. And this has really taken off in the last few years. So all of that is coupled with lots of different diversity in this data. And pretty much up to this point, we've been working with structured health data that we actually set out to collect, and we make the parameters of how we're going to collect that data. But as we started to harness existing data from all those different data sources, we realized that we have data everywhere. And I love this quote, data everywhere, not a thought to think, because we didn't know exactly what to do with this data. So at the same time, we had increasing computational capacity. So some of you will remember those little disks at the bottom of the screen there. We've moved well beyond that. We're in cloud computing. We can process data that we couldn't even dream of 10, 20, 30 years ago. So the fundamental methods for AI really were established many years ago, decades ago, the theory behind AI machine learning approaches. But it's the increasing computational capacity and data that we have that we didn't have before that's really changed. So that's why we're in the state now where AI is so hot. But we do really need to go back and understand some of the fundamentals of AI and machine learning to understand what we're actually embarking upon and why it might be important. So the first thing is I'm not going to try and give you a definition of what artificial intelligence is, because it's actually many things. You will hear various definitions, something along the lines of programming something without explicitly programming it, etc. But it's an umbrella term, meaning it has lots of different things under the umbrella. Here's just some of the examples. It includes machine learning, but also includes software, automation of tasks, algorithms, natural language processing. So it's a big umbrella term. So it's really important to think about what exactly you mean by AI or what the intended application is. What I'm going to focus mostly on is machine learning terminology. And there is a great paper that you were provided with that goes into this terminology, specifically in the context of public health, which is very useful. And you may hear different types of machine learning methodologies. In fact, you may learn some of these specific ones, random forests, neural networks, etc. That type of classification isn't as useful in terms of identifying what the task is that this machine learning algorithm is trying to do. So these are the three buckets that are most useful when thinking about machine learning applications. So the first one is supervised applications. And this would be something, if you've worked in health data in any way, something you would be actually quite familiar with. The idea that you're fitting variables together, trying to find patterns, correlations. You have some exposure variables, some outcome variables, and you're trying to find a way that they relate together. Many of you may be familiar with regression techniques, and this is actually a very popular application of regression techniques. We have variables that go in, we've specified an outcome, and we're trying to fit them together. And so logistic regression, for example, or any other parametric regression. Machine learning is a bit more than that in that those regression techniques have very constrained aspects to them, very specific distributional assumptions, and make a lot of decisions on whoever's programming it in terms of what variables go in. As we start to relax some of those a little bit, even though we're still trying to find associations with variables and outcomes, we get into some of the more complex methodology. So you can have a supervised random forest, which you will probably get some experience running, or an advanced neural network that's also supervised. It just means that the variables and the outcome is somewhat stated in advance, and you're trying to find a relationship for that particular problem. So this would be the case for a lot of our predictive analytics. So unsupervised methods are actually quite distinct. These are methods where you're trying to use the properties of the data to find patterns or correlations. And again, you can have simple unsupervised methods, or you can have very complicated ones. So a simple approach would be a principal component analysis or some kind of other cluster-based analysis. You can go up to k-means clustering or even deep learning methods. And so unsupervised methods are quite distinct and actually in some ways quite new for public health, in that we're not specifying a priori what's happening, we're not hypothesis testing, we're trying to use the patterns of the data to glean information. And there's some very specific applications where these approaches align very well. And then the last bucket is semi-supervised, and often actually you will see supervised and unsupervised approaches go together. And that is maybe an unsupervised approach to reduce data down to meaningful clusters, and then once you have that, you would run a supervised approach thereafter. So when you're thinking about machine learning applications in health, think about these types of buckets and see if it's falling into each of these. And the technical aspects of running these methods can range from very straightforward or more straightforward to very complex, depending on which approach and what data you're dealing with. So with that in mind, I want to talk specifically about deep learning. Again, something you might hear a lot about if you're hearing about AI and machine learning. So deep learning really goes along with the unsupervised methods, but in this case, we're really talking about large volumes of high dimensional data. So you can't run deep learning approaches when you don't have a lot of data. They are data hungry approaches. You also need extensive computational power for these approaches. And this is really due to the fact that these methods rely less and less on a person programming specific decisions and really on the data driving those decisions through pattern recognition. So you'll have multiple machine learning models, for example, multiple layers, and so they're quite a bit more complex. This methodology was founded in part at the University of Toronto by Jeff Hinton, and him and his colleagues have written a review methodology that's really nice if you want to hear more about deep learning methods. I'll give you some examples later on so you can see how this works in practice. So again, to just go into some of the examples I've told you, supervised, unsupervised, semi-supervised, what does that actually mean? So for example, the unsupervised approaches are some of these clustering approaches. When would you use these in a health space? Well, in public health, you would typically use these for surveillance purposes, maybe hotspot detection, case ascertainment, when you're trying to put clusters of things together and you're actually not sure what you're trying to find. Maybe it's an emerging situation. Maybe it's a public health threat or a health threat that's emerging. Or maybe it's surveillance and you're trying to identify outliers. Those would be some of the examples for unsupervised applications. For supervised, this would be, again, some of your predictive analytics, trying to identify diagnostic algorithms, for example, for mammograms or other health effects, maybe trying to predict some health outcomes from wearables. These would all be different types of supervised approaches. And you can see the examples, the different types of models that can be run. So naive Bayes, neural networks, support vector machines, decision trees. These are just different types of analytic tools that you can run to achieve these supervised tasks. Now, compared to regression, which you might be more familiar with, they generally do not rely on linear assumptions, do not have strict distributional assumptions, can handle more interactions. So they are a bit more flexible. But again, that flexibility is only advantageous if you have data with lots of this complexity in it. So sometimes when you see comparisons between machine learning models and regular regression models from a statistical sense and they produce similar results, the most likely explanation is that they were running on similar data. They weren't data that had that complexity which these models really thrive in. So the other thing to be aware of if you're coming from more of a statistics or epidemiology background is that different disciplines, different terms. So these disciplines sort of grew up together. And I'll say that the machine learning disciplines, not exclusively, but for the most part, really thrived in sectors outside of health. And actually a lot of the AI machine learning advances are happening outside of health in our everyday life. You probably interact with them every day without even realizing it through all your different devices and email and Netflix and all kinds of applications. It's happening all around us, and banking. And so those advances have happened at a very fast pace. And it's starting to make some advances in health as well. But because the disciplines sort of grew up separately, although simultaneously, but they are closely related, there are some different terminology and traditions. So if you're starting to engage with some of the literature, it is important to realize that there are different terms for similar concepts, not always exactly the same, but similar. So here's a list of topics that you might be familiar with in public health or stats or epidemiology, and where it might exist in computer science terminology. So things like features are called, we would know them as variables. Labels, outcomes, one-hot encoding, which actually is just a different term for dummy variables or indicator variables, learning, fitting, precision, which is actually, if you look at the definition, would be our definition, what we would know as positive predictive value. Sensitivity would be what computer scientists would call recall. And there's lots of these little nuances back and forth. So when fields seem seemingly different, they actually are capturing the same thing. They have different terminology and sometimes put emphasis on different measures compared to others. So let's move to what the advantages of these approaches actually have. So I've told you that the evolving data environment's happening. I told you that we have computational power. We have these methods that may be a little more flexible. What are we trying to do with these methods? Why are they becoming so popular? So Eric Topol wrote a really nice review in Nature Medicine on where these methods can have benefit when it comes to medicine. So in summary from that article, we see that perhaps these algorithms can help with reducing clinical and diagnostic errors, mistakes in treatment, wasted resources, inefficiencies in workflow, time, inequities in terms of who's getting what treatment. So the common thread there is that if there are these algorithms that are helping support decisions, we could potentially spend more time with the patients. We could have checks and balance for some of the decisions that are being made, maybe some standardization for clinical practice, which is actually quite variable at the moment. And so these are all suggestions of where these machine learning could help. And of course, it's not perfect. Most of the implementation side of machine learning is still a very early field, and there's lots to be developed in this case. But you can see that this is really just about making better use of data to support decision making and some of the tools to help do that. Now think about this from a health system or a population health perspective. How could machine learning actually provide benefit? Well, first of all, when you think about health and public health, the determinants of health are broad, varied, complex. I would say even more complex than a constrained clinical environment. And so if we're trying to gather information from multiple sources, that can actually be quite difficult. And then what do we do with that data? And so if we have methods that allow us to gather data from these multiple sources in a bit more flexible way, that could be a significant advantage. We also have similar challenges with matching resources to need. And again, in public health, we have a strong tradition of doing this using data for decisions, for applied decisions, actually. We've been doing this for years and years. But are we using predictive tools? Are we using tools to the best of our ability? And of course, there are emerging situations that happen in public health, and are we responding in the best way possible? Sometimes we do need intelligence that's gathered at a scale that can be done if it's algorithmic. And so these are some of the challenges that we can overcome with these methods, and I'll talk about some of the barriers at the end of the presentation. So this, again, is another paper that really describes some of the application aspects of big data, precision public health. And precision public health is this idea, building from precision medicine, precision medicine being right treatment at the right time for the right patients. Well, you can take that application to public health, saying right interventions for the right populations at the right time. But of course, it's not a perfect analogy. There are some challenges and some risks to doing that. But what I think this slide nicely shows is where can we go when we open up our mind to what data we can actually use and process and gain intelligence from? And more importantly, can we gain that intelligence from the individual, relationship, community, and society? The community and society is where we probably have the most potential when we're starting to get information from our environment, from lots of different sources. And again, we don't have experience typically working with these types of data, some of it unstructured, highly variable, highly dimensional. These offer some tools to help us deal with those types of data and some potential. So one of the most important take-homes I'd like you to glean from this talk today is getting much more specific about the applications. So I've talked about lots of different types of models and clustering and predictive and all these different bits of machine learning that are really interesting, and also statistics. But I think the most important part of applying these methods, or any methods for that matter, is understanding what we're trying to do with them. And there are these 4 categories, and there's a paper of reference that describes some of these categories in a bit more detail that I think are really important. So the first one is descriptive, and that's about understanding what's happening around us. Then there's predictive, and that's about understanding what's coming next. There's causal inference, which is about why things are happening and understanding the mechanisms. And then there's prescriptive, which is about telling us what should happen, or doing different intervention scenarios to understand the what ifs and the implications. And for the most part, even forget about machine learning, even if we just imagined it didn't exist. Sometimes we blur these things together, and that's actually what creates confusion and complication. Then you layer on different analytic approaches that tend to go in each of these buckets, and it can get pretty complicated. So I hope by today it's quite clear the different types of applications, and there's a good understanding of when you should use which tool for which application. So let's go into some of them in more detail. And I'm going to start with descriptive, or in public health, as we would know, surveillance. And again, public health has been doing surveillance for 600 years. The definition of surveillance, which we have up here, is a definition from WHO, which is about continuously, systematically collecting data, analyzing and interpreting it, putting it into some kind of product for the purpose of action. And so again, we've been doing this for a long time. The difference now is that we have different analytic tools that are starting to make a presence, some of them in the form of machine learning, but the actual fundamental concept of what we're trying to do has not changed. In healthcare, often this is seen as quality improvement or performance measurement. The idea that you collect data, you analyze it, you report on it, and it should inform some action. So let's look at an example of a deep learning approach that's surveillance in sort of a public health relevance. So this is a text-based spatial event detection approach, and it's from Daniel Neal, who runs a pattern detection lab and has lots of interesting work in this area. So the example here is the idea that when people present to emergency departments, they have their chief complaints recorded. It's recorded by text, and that's recorded in some way. And without using any type of technology, there might be a situation you can imagine if there's an emerging infectious disease where some ER doctors or nurses would start noticing that there would be people showing up with symptoms, and someone would report that to some public health authority, and there would be some investigation. And this probably actually happens to some extent within every hospital. So the idea here is to use natural language processing to try and actually develop a text-based spatial event detection. So detecting these symptoms as they're written down, spatially mapping them, and scaling that up to actually characterize and localize new outbreaks that need investigation. So a couple things to point out in this example. So first of all, it's exploiting the richness of data that is really difficult to do if you're doing this manually. By algorithmically allowing the text-based detection approach, we can process many records, and we can scale that up at a societal scale. So you can imagine you could do this in hospitals across province, country, very easily, as opposed to manual sources. And of course, they aren't error-free. They would still need to be investigated, but that would be the case for other approaches as well. And the other thing that I really like about this example is that it's showing how you can integrate multiple sources of data. So not just the symptoms, but where those symptoms are occurring, and maybe lots of other elements layered within there. So you can actually get a very comprehensive picture of where things are occurring, not just what's occurring at a scalable level. So one example of an unsupervised approach, but really used for descriptive or surveillance purposes, not for necessarily prediction. This is another example, again, of an unsupervised approach applied to injuries. So in this particular example, which was in the UK, they were interested in studying patterns of injuries in a particular areas of London. So they had a problem with pedestrian injuries, and instead of saying, well, we have a problem, this is our way to fix it, they tried to get an understanding of these injuries without pre-specifying specifically what these subgroups may be. So they used an unsupervised approach. They analyzed all the injuries that were happening in the regions, a lot of technical detail here. But they found that there were these distinct clusters. There were injuries happening when late night footballers were leaving the football field. So that's quite a different scenario than people running very early in the morning at 5 a.m. before they go to work, or Sunday afternoon riders. You have the cyclists in Westminster. So after they found these clusters, they started to think about different prevention strategies that would work on these different subgroups. So obviously people leaving a game at night, maybe there are other factors that are at play that can be controlled. Maybe the people running in early in the morning, it's a lighting issue. Maybe Sunday afternoon, there are speeding issues. There's lots of permutations. But the idea with an unsupervised approach that you can actually glean some insights that help inform action. Again, this would be descriptive. So this is a last example on this particular piece. And what's interesting about this is the idea of convolutional neural networks. So this is a methodology which allows you to make sense of an image. And one of those images that may be relevant would be learning about our environment. So right now, the built environment's a very important topic in public health. We study lots of attributes of the work of built environment, and we know that it's actually related to lots of health outcomes. So the idea of this is actually taking a picture of a built environment, and this could be understanding not just the density of the area, but green space and other aspects of the environment, trying to characterize it using machine learning methods. And then with that, understanding how those features relate to specific outcomes. So again, this could be a sort of descriptive task, but you can also see how some of this could be integrated into a predictive model or a causal model, which I'll talk about in a few moments. So one of interesting aspects of visual analytics as it relates to the built environment. We hear a lot about visual analytics and machine learning when it comes to diagnostic measures, x-rays, radiology, but it also has a place for understanding complexity in other areas like our environment. And this example is another surveillance example, but it also integrates predictive analytics as well. And it was recently published, and this is an example of how we can use social media data for surveillance purposes with Sentinel, which is a syndromic surveillance system. So a syndromic surveillance system monitors syndromes, so how people are feeling, cough, fever, etc., to try and get a handle on outbreaks before they, as they are emerging. So what did they do in this article? So they took data from Twitter, RSS newsfeed, and they, what you can see is that they actually extract the data, and you can start to get a sense of the complexity of the pipeline. They understand where the data is coming from, process it, etc. And they verified what they were getting from the social media data against CDC lab counts, actual observed outbreaks that have been verified. That's what they call the ground truth, which would be a sort of validation. And you can see that the data is coming in, so that could be the surveillance aspect, but then they actually have a predictive element at the end to try and see where it would be going based on where it's been. So again, lots of complexity. And again, I demonstrate this to demonstrate how complicated the pipeline actually is. So a lot of the work in this area is about getting that data in, processing it, and making sense of it. And there's lots of different technology just focused specifically on this. But there'll be some sort of API that takes all that data in, and lots of widgets and map that make it useful for action. So this is an example with some of the data that's coming in. They're able to process it, spatially detect it, and actually map it to see that there might be events coming in certain regions and detect whether it's higher or normal than what is expected. And you can see the entire pipeline here. So now we're starting to get quite a bit more sophisticated, other than just using complicated data, but actually putting it in a pipeline that includes unsupervised and supervised methods when we come to the prediction piece. So I now just want to talk about prediction applications specifically and try and just get some sense of how this is working in health-related environments. So if you think back to where we used to get our data for risk prediction models, because risk prediction models have actually been around for a long time in health, they used to come from cohort data or clinical trial data. So we would set out to collect these data, we'd make sure that they were measuring the things we wanted to measure, and then we would put those things in our models, specifying what's going in, specifying the outcome. So a very supervised approach. So what's been increasing in frequency is garnering this data from electronic health records, and I talked about a little bit this from the beginning. And this can be combinations of collected data, clinical data. Sometimes that data is coming in real time, sometimes it's spilling data. And so the methods, again, that we're seeing increasing are regression-based, certainly, but we're seeing an increase in machine learning, deep learning methods, and ensemble methods, and we're starting to see combinations of supervised, unsupervised, and semi-supervised. So let's go through one example with that piece in mind. So this is an example of deep learning algorithms that happen in the context of electronic health records. And again, I want to draw attention to the pipeline here, because this is where the complexity is and where there's differences from some of the methods we've seen before. So we have health systems that collect electronic health records in various forms. You come into the hospital, lots of people are collecting data from you at different points in time for different reasons. And not everybody has the same data collected, because it depends on why they're coming to the hospital and what circumstances happen when they're there. And so they have an example here for each patient, and you'll see that the patient is, lots of things are happening over time. They come in, maybe they get a test, maybe they get sent for another diagnostic test, a lab test, and eventually are discharged. And so this paper really talks about developing algorithms using all the data from the electronic health records based on all those different points in time. So you see an algorithm for readmission risk, inpatient mortality, diagnoses, any prediction. And what's interesting about this paper is that it is significantly more complex. So any risk algorithm you would have seen up to this point, or even up to about 10 years ago, would be predicting one thing based on one data source. So here you have lots of data inputs coming in, you have lots of time, so one patient can have multiple predictions happen on them. You have recurrence, and you have to have a way to integrate multiple prediction models together. So I hope you can see that this is actually quite a bit more complex. It's actually not feasible that someone is programming all these things or putting these things together, that we actually do have to rely on machine learning and algorithms to achieve this level of complexity. In this paper in particular, they did talk and attempt to highlight factors that were important for the prediction. So this has often been a criticism, the black box element, which I'll talk about again at the end. But they made an attempt to actually state what the most important factors were for prediction. So if someone's reviewing this, they could say that makes sense. This is interesting, and we have lots of examples of interesting algorithms like this being developed every day, really, in the literature. We don't have a lot of studies looking at the impact of these algorithms. We don't actually know how they're being used or if they have an impact on improved patient care. And so that's something that we definitely need more of to understand whether these algorithms are helping inform decisions or are they just another data point and we're seeing similar outcomes. So last kind of bucket I'm going to talk about is the causal inference piece. And just a warning, this is a bit more complex than anything else I've talked about up to date. You may or may not have a background or in causal inference, but I'm going to try and get you up to speed for the purposes of understanding what we're talking about here. So first, we talk a lot about prediction, especially in the context of machine learning. But we don't actually talk a lot about explanation. I mean, I've showed you that the prior example tried to show you the variables that were most important for prediction, but that's very different than understanding why things are happening from a causal inference perspective. So is something actually causing that outcome? If we took that away, would the outcome not happen, for example? This happens in regression as well. This is not a problem that's unique to machine learning. We have the same analytic tools, like regression, being used differently depending on the aim of the task. And so if you're using it for descriptive purposes, it may make sense. If you're using it for causal inference purposes, you can use it the wrong way, and then as a result have wrong inferences. So it's really just important to memorize that, to remember that prediction models are not causal inference models. They never were. And it doesn't matter if we have a new way of doing those models, they are still not causal inference. However, they can be used to carry out causal inference if they're used conceptually and in the appropriate way. So this is my one slide on causal inference, and you can ignore it if you want, but I'm going to mention it anyway, and hopefully this helps you understand the example I'm going to show you. So one of the ways, there's lots of ways we can conceptualize causal inference and lots of debates, but one of the ways is this idea of the counterfactual, which was proposed by Rosenbaum and Rubin in 1980. And the idea behind this counterfactual framework is that you create a counterfactual situation where the exposure is not there. So imagine everything about you stays the same, and you have this hypothetical universe where the only thing is different is the exposure of interest, the thing that you're trying to understand if it has a causal influence, like a drug or smoking. And we can't actually observe that in observational data. That's called the fundamental problem of causal inference, because we don't have a parallel universe where we can repeat your life minus the exposure. So we try and do this using analytic methods to try and balance groups that have or do not have the exposure with the idea that this gives us an estimate of causality. That's what we do in randomized studies. And it's one mechanism by which we can assess causality. And we can do it in observational studies using lots of analytic techniques, including inverse probability treatment weights or propensity methods as examples. So where does machine learning fit in? So first of all, machine learning, I think, gets criticized for not being causal. But again, if it's a prediction model, that's not what it's actually supposed to do. It's trying to do predictions. So this is an example, however, where they are using machine learning methods in a causal framework, and it's appropriate. So this particular example, published in the International Journal of Epidemiology, is looking at the impact of social housing on mental health. And again, there's lots of complexity to the model, but they are able to look at comparing those with and without social housing to see what the impact would be in causal health and mental health, and to see if that impact is causal. So they apply the marginal structural model, which in and of itself can be regression-based. And they use inverse probability treatment weights to try and create that counterfactual scenario to test their causal hypothesis. That's a simplification of what they've done. But where the machine learning methods fit in is that they used multiple types of models, which they called base learners, and multiple variables and features known as super learners. And with that, they use machine learning methods to try and create the best model possible to create that balance analytically. And once they create that balance, they can carry out their causal inference. And there's been lots of investigations and some suggestions that when you employ these methods in this way, you can actually create better balance, which should reduce the likelihood that you have any unmeasured confounding, which is biasing your association. So again, one example where conceptually we haven't really changed this. We're still sort of approaching the problem in a potential outcomes framework for causal analysis. But instead of applying regression to try and create balance analytically, we're bringing these machine learning models, which are able to handle more variables. We're looking at lots of models and basically a summary of those models to try and get a better estimate. So now I think it's time for a break. I'm sure you need one. And so I'd like you to take a moment and try and reflect a bit on what's out there based on what you've heard right now. So you have been provided with 3 papers, and I only want you to read the abstracts. The point here is not to get deep into the technical details. You will have time to do that as you're working through these methods during the applied exercises. The point here is really just to try and step back and see if you could recognize some of the things I've been talking about in some of the examples that I'm showing you. So I want you to read them through again, abstract only, and don't get hung up on any technical aspects. Just try and see if you can classify the approach as supervised, unsupervised, or semi-supervised, and try and see if you can classify the application as descriptive, predictive, or causal. And I didn't give you prescriptive analytics because I think that's out of scope. So descriptive, predictive, or causal. And maybe you can't make a decision, or maybe it's both or combination, and that's fine as well. So just take about 15 minutes, speak in pairs or threes if you like, try and discuss with the group, and then we'll come back after you've had a chance to think through these and finish up the rest of the lecture. Welcome back. I hope you enjoyed digging into some machine learning applications. And I hope from the discussion that you really got a sense of, first, the variability of these applications. So again, one thing I want you to take away from this lecture today is that this is not one method. These are many methods and many applications. Also to get a sense of when these applications add value and when maybe they don't. So it's not the hammer for every nail. And definitely you can start seeing where they are adding value. You can see in the examples I gave you, it's when the complexity goes way up, significantly more so than maybe some aspects you've seen or been working with before. That's when the value is going to be most likely significant. And hopefully you also are getting a sense about how the results are communicated, which is interesting. And again, because of the disciplinary traditions, might be different than what you're used to seeing. Okay, so for the last bit, we're going to talk a little bit more critically about how these applications are being applied in practice, and some pros and cons of these applications, and some good things to be aware of as you become a critical consumer of these methods and maybe start to use these methods a bit more yourself. So the first thing, which I like to call the elephant in the room, is measurement error. And I haven't talked about this at all. I've talked about the exciting aspect of getting all this new data from different aspects, but I haven't really talked about data quality. And I want to emphasize that regardless of the analytic approach, it will always be affected by data that's of poor quality, high heterogeneity, or measurement error. So what I mean by that is that it doesn't matter which tool, no matter how fancy you're applying it to, if your data has biases or errors in it, that will reflect in how the algorithms come out, the insights that are gleaned from the data, the causal inferences you're trying to make from it. So measurement error is a problem that doesn't go away. And in fact, because you're dealing with data that's maybe a bit more heterogeneous, newer, we haven't worked with it before, it may be even more of an issue. So it's a really important piece to make note of. It's why those pipeline slides I was showing were so important, why there needs to be data quality checks and sanity checks throughout. And often, multiple coders, et cetera, are required, especially for some of the initial applications of the data. So an example, when I showed you that Sentinel paper where they were taking all of the data from Twitter and RSS newsfeed and kind of popping up all these emerging outbreaks, one of them that came up was Bieber fever, which isn't actually a disease, depending on who you ask, but not the type of disease they were trying to get at in terms of infectious disease outbreaks and emerging outbreaks. But it's a fever, it was trending, went viral, it got passed on, and so it's something that needed to be checked. So really this is a noise in the data, and if you're working with this type of high dimensional, especially real-time data, there's going to be a lot of noise signal. So there needs to be a lot of fine-tuning to understand when you're actually going to act on the noise that's coming up. So again, the volume and the size of the data does not negate the measurement error, and that's something that's really important. The other pieces are secondary sources of data, so data that you didn't set out to collect, and data that you did set out to collect, for that matter, can have selection biases in the data. And I'm going to talk about that more in the next slide. But the volume noise piece is really important. It is one of the biggest challenges, especially if we're going to invest resources in reacting to these signals. And so there do needs to be thresholds and discussion on when you act on when signals come out and if they're real. So the other piece I want to talk about in the context of measurement error is that there's different types of measurement error. So the first one I'm going to talk about can be random error. And this is a study that I worked on that actually looked at the impact of different types of error in a prediction context, which is actually really different than measurement error than we typically talk about it. So random error are errors that just happen randomly. They don't have a specific direction or affect a specific subgroup. They could just be, something that was entered incorrectly, and it doesn't have a specific reason as to why that happens. And that can happen anywhere. And then there's systematic error, which is thought to be more serious, although in the prediction context, not necessarily so. So systematic error is when certain groups, for example, maybe over-report or under-report specific factors. In this case, we were looking at diabetes risk and looking at over and under-reporting of height and weight and how that relates to diabetes risk. And there's been other papers as well, and I put a couple citations here if you're interested in this. But basically, the take-home message is that random error and systematic error have the potential to influence the performance of risk prediction models. And I mention this specifically because most people are used to, especially if you have training in epidemiology, you're used to thinking about measurement error. We actually think about it all the time, and we know it's there, and we try and control for it. But we don't necessarily understand how it operates when you're predicting risk versus if you're just thinking about an exposure-outcome relationship. So we actually found that random error can affect your ability to make predictions. And if you think about it, that makes sense, because the more random error there is, you could think of people, let's say, that have the event and don't have the event, and you add lots of noise to that, it actually becomes very difficult to be able to tell between who did and who didn't have the event. Interestingly enough, with systematic error, sometimes you could still rank who's high risk at low risk and who's low risk, because people tend to systematically report things in a certain way, and the algorithms can learn this as well. It doesn't mean it's a good thing, because you can still have bias when you try and apply the algorithms in other settings, but you can often still get good performance characteristics even in the presence of systematic error. And the other interesting thing about prediction, which is really distinct from exposure outcome relationships, is that if you have other variables in the model that are accounting for that variation, that are highly correlated with the variable that's error prone, you can sometimes mask the impact of the error of that model. And that is not the case when you think of exposure outcome relationships, because you have confounding factors to think about, and it can be quite complicated. So the last point is that there was actually a systematic review on how prediction models account for measurement error, and not surprisingly, the reporting of it is very poor. And I would say that's also the case for a lot of machine learning applications. We don't often hear a lot about the quality of the data, and that's a challenge, because if the data is fraught with errors and random error or systematic error, it's definitely going to affect the performance of the algorithm. And so that's something that needs to be improved upon. And you need to watch out for as you're looking through some of the results from some of these papers. So I mentioned we were going to talk about selection bias. So this is the bias that keeps me up at night because it's very strong. So many factors that can determine whether people participate in certain data sources can result in bias. And so lots of examples you can think of. Examples, social media users might be younger or have more education. People that use wearables might be systematically different from those that don't. Lots of people that enter healthcare just by being there already are different than people that may not have access, for example. So there's all these kinds of factors that drive your participation to a data source. The algorithms are going to learn based on that data. And if they learn based on that data, they can also bring in the biases that those data we're holding. And this is really problematic if we're going to then use those algorithms to make decisions. We can either make wrong decisions or we can perpetuate biases that exist in the data. And so there's lots of people thinking about bias and fairness in machine learning and trying to correct for this. I think in public health, we have a unique example, a unique opportunity to think about this as well, because again, we think about it all the time because we're thinking about data in populations. We're always thinking about who does our data apply to, who does it not apply to, what are we missing in the data? In epidemiology, the gold standard when it comes to selection bias is try to identify all of these biases as much as possible and conceptually think through the biases that may exist. If possible, you can control for them, which may be difficult to do because you may not have the data on the bias that you require in the data set that you have access to. If you do have ability to adjust for biases, you can account for them. There are different methodologies to do this. And there's a field called quantitative bias analysis, which allows you to make corrections for different biases in the data, or at least understand the impact of them. And that's really where the last bullet point comes in, is trying to do at least sensitivity analysis to understand if these biases did exist, especially if you had an idea of what the biases might be, what impact they're actually having on the results. There also needs to be thought through biases in the validation approaches. So a lot of machine learning approaches are validated in other subgroups. Often not specifically, though, in certain subgroups. So you will see this in some applications where you actually take an algorithm and take it to a population you know is different, may not have the characteristics, maybe they have the biases that you're worried about, and present in the data, and try and see if the algorithm actually has the same performance characteristics. And if it's not performing in certain subgroups, it's probably an indication that important factors are missing from the algorithm. So selection bias, again, is something that's really important. It doesn't go away just because you're applying a different methodology. And if anything, you have to think about it even more if you're trying to derive an algorithm that's come from the data that you're going to apply and make decisions on. So the other piece that you'll often hear with machine learning is the black box nature. And again, this paper comes from Prosperi et al. Article, which was circulated. And this is the idea that we have some algorithms that are simple, like linear models, even though I think that we think simple, and sometimes there's more complexity than meets the eye with a lot of these applications. And then we have these very complicated models with lots of layers and that you can't really trace back to 10 variables, let's say, in a simple way. So they're considered black box. And there's some apprehension of using a model which you don't understand is happening. And to some extent, there's some truth to that, and there's some really solid attempts to try and overcome that by making explainable models or trying to break down elements of the model. So you don't have to see every piece, but can you understand what the top factors are for influencing the outcome? One challenge I'll just put out for this is that if we try and focus too much on explainability, we might be confirming our cognitive biases that we have already. So if the model is telling us something that we think it should be telling us, then we think it's okay. If those top 10 factors are not factors that we thought were important, then we question it. And so there might be some challenges with that approach because it's pretty crude. I think the most important thing is that we assess performance in different subgroups, assess performance in different data sources. And the more and more that we see the data is consistently performing, the more and more we can trust the approach and trust what the models are telling us versus trying to understand whether what's in the model. Because I think, as is the case with lots of other machine learning applications we see outside of health, it's not really about understanding specifically, it's about being able to do really well at predicting what's coming next. And that information is useful to know for decision making. And so the more we test the impact of these models in real life situations, the more we trust the models, I think that's the most important piece for decision making. And this summary just reflects that point. And it's really the conclusion of the Topol article I mentioned in the beginning, which is a call for more impact evaluation. So the quote, "It's not yet known how well AI can predict key outcomes in healthcare settings, and this will not be determined until there's robust validation and prospective real-world clinical environments with rigorous statistical methodology and analyses." So what he's really calling for here is let's put some of these algorithms in practice in a safe way, where the risks are low initially, and study and see if it's actually making a difference. Is it improving efficiency, improving outcomes, improving health? Is it resulting in increased disparities or decreased disparities? These are all things we don't know unless we start testing the application of the algorithms versus specifically the methodologies, those methods will always evolve. I'm now going to summarize what we just talked about and what I hope you took away from today's lecture. So first, we covered some fundamental concepts related to AI and machine learning. So we really talked about what it is and all the different elements of AI and machine learning and tried to distinguish between the types of applications. So hopefully you have a better sense of what supervised, unsupervised, semi-supervised methods are, and have a sense that these methods can be applied in lots of different ways, including for descriptive analysis, predictive analysis, and causal inference. We didn't talk specifically in detail about prescriptive analytics. It's sort of an advanced topic, but I want to include it for completeness. So as much as possible, I hope that you can start getting some specificity about what the applications are and why machine learning approaches may or may not be the appropriate tool for that application. As much as possible, as we get clarity on this, we'll have much more success in the application of these methods and get a better understanding of when they're actually adding value and when they may not be the best approach for the method. And that's true for all types of analytics. And then finally, we ended on some critical issues related to bias and measurement that continually need attention. I really just touched the surface when it came to these issues. These are very complex issues that continually need attention and continually need oversight in terms of applying these methods. So measurement error and data quality are important for any analytics that we run on these data, as well as considering the impact of the selection bias of the data that we're looking at. Thank you for listening.